Hello everyone, and welcome to this video titled Limits at Infinity and Asymptotes. So in this video, I'm going to be taking you through a preview version of a Knewton Alta Homework Assignment that is also titled Limits at Infinity and Asymptotes. So please understand that this is a preview version, so the questions that I work on in this video may not be exactly the same questions that you see when you work on the assignment yourself, but the objectives should be the same and the methods used to solve problems should be similar. All right, so here we are at Knewton Alta's site. It is a preview of, in this course, this is called section 4.6. Again, it's titled Limits at Infinity and Asymptotes. So in the upper right hand corner, you should see a mastery bar, and that shows you how far along you've gotten in the assignment. Next to this, an activity log, and if you click on that, it'll show you all the objectives for the assignment. So this particular assignment is broken up into 6 objectives under 2 headings. One is limits at infinity, and the other oblique asymptotes and curve sketching. And back on your main screen, you have a current objective stated. Then beneath that, a question related to that objective. And at the bottom of every question, you should be able to find a feedback option. So if you see any errors in the question, or maybe errors in the answer explanations after a question, you can send feedback directly to Knewton support, and hopefully someone will get back to you relatively quickly with ways to fix your issues. I hope it's understandable that you will not have this instructor cheat option. Right? This is for instructors only to fill in blank answers, fill in correct answers, and I will not be using this in this video. But you should find a more instruction option. So if you're working on an objective and you forget the material or you need to brush up on things, click on more instruction, open that up. And you'll be taken to some reading to do or videos to watch or both related to that particular objective. And hopefully having that instruction up will help you get through the questions in the assignment. All right, so first objective here is understand the meaning of a limit at infinity and horizontal asymptotes. Okay, so first I'll quickly explain what these are and then come back to the question. So first, these limits at infinity. So this is simply pretty much discussing the end behavior of a function. Where is the graph of a function going to go? Where are the outputs going? To the far right and the far left. So you have your right end behavior. So you'll be taking the limit as x approaches, again, let's just say x is my input variable, independent variable for some function. So if you're talking about the right end, think of the xy plane, That means, going to the far right, the value of x approaches, positive infinity, gets larger and larger of, some function of x, some expression that depends on x. This should be referred to as a limit at infinity, right? X is approaching this infinity. Again, not a value. Infinity is not a number, but this explains the concept. This describes the concept of going to the right, increasing the input forever without. And then your left end behavior is simply look the other way, right? So think of the x-axis, values of x I'm plugging in, values of the input variable. So my left end behavior is, the limit, evaluating the limit as x approaches negative infinity, right? Plug in larger and larger negative numbers, or smaller and smaller numbers if you think about how a number line is structured, but the magnitude of the numbers is getting larger and the value is negative, the sign is negative. Yeah, and that's all a limit at infinity is see what happens to the value of a function as the input gets very large positive or very large negative, right? At positive infinity, at negative infinity. Now they also mention in the objective there horizontal asymptotes. So if one of these limits, so either the limit as x approaches positive infinity of your function is finite, so let's say L here, where L is not infinite, right? L is finite, or again, either one, if the right end is approaching some value, or the left end, and say limit as x approaches negative infinity of f of x, is also some finite value. If either one of these occur, right? This is or. Then the line y equals L, right, the horizontal line, is going to be called a horizontal asymptote for the graph of the function, I'm calling f here. Okay, so in a picture, real quick in the lower corner here, so again, you're at your xy plane. Now say L is some value here on the y-axis. So on the horizontal line, y equals L would be considered a horizontal asymptote if the graph is approaching. So say the graph of my function is doing this to the far right. So is the graph of f, this little curve I'm drawing here. So as I move to the far right, as x goes to infinity, the graph is approaching this line. And maybe to the far left, it's doing this. So one note I'll make, maybe I'll pull up another page here. As long as one end is approaching a horizontal line, you got a horizontal asymptote, right? And there are two ends, right and left end. So you can have no horizontal asymptote, one horizontal asymptote, or two, but no more than that. So a couple notes about horizontal asymptotes. There can be at most two horizontal asymptotes, and one to the right end and one for the left end. Also, a horizontal asymptote can be intersected. Horizontal asymptotes can be crossed by the graph of the function. It's just as long as the graph of the function is getting closer and closer to becoming this horizontal line on either end, you have a horizontal asymptote. So again, they can be crossed by the graph of the function. Right, so I'll show you what I mean with some pictures here. So again, here's one with no horizontal asymptotes. Say like your polynomial functions, like here's a cubic, where you see the right end is not approaching some horizontal line. Left end, the graph's not approaching, some horizontal line. So a polynomial function, there's others too, but that's an example of a function that would have no horizontal asymptotes. So here's an example of one that would have just one. So maybe your exponentials, like here's some exponential function with a base larger than 1. The horizontal asymptote, I'll just dash it in here, will be the x-axis, y equals 0. Right, so on just the one end though. Now you could have one where the graph is approaching it on both ends, but again, as long as one end, as long as the graph on either end is approaching a horizontal line, you have a horizontal asymptote, right? So again, I could have just the one. So again, here's L, y equals L. And yeah, you could have a graph that approaches it on both ends, right? Say from below over here, curls down a bit, comes back up, and approaches it again over there. So still just the one horizontal asymptote. But you could also have two, one for each end. So I'll call this L1 and down here L2. So you could have two horizontal asymptotes. And so maybe my example graph here, maybe the graph is approaching this line y equals L2 on the left end as x goes to negative infinity. And then maybe this is happening on the right end. Now I told you it can be crossed. Right, so maybe it's doing that, but still, you can cross these horizontal asymptotes. What's important though is as you go to the far right, the distance between the graph and the line shrinks. Right? So again, no asymptotes, no horizontal asymptotes. You can have one on just one end or one on both ends, or a different one on both ends, but no more than two horizontal asymptotes, and they can be crossed. All right, so now we got that. What does it mean to take a limit at infinity? What does it mean to have a horizontal asymptote? Well, let's take a look at our problem now. So it says for the function given below, use a calculator. So I'm going to go to Desmos, one I've used in many videos before, desmos.com, or other evaluation tool to evaluate the function at increasingly larger negative values of x. So this is the limit as x approaches negative infinity for this function here. So I'm going to go to Desmos, enter this f of x equals x plus the square root of x squared plus 5, and then plus 4 after. So I already got Desmos pulled up. So the function we're given is x plus the square root of x squared plus 5, and then, plus 4 after. Now, if you look at this, I'll zoom out a bit here. It looks as though, as I move to the far left, the graph is definitely approaching something, right? It's definitely getting horizontal as you move to the left, not going up forever or down forever. It definitely has some horizontal asymptote, right? And even just looking at the points I had here highlighted, it looks like it's approaching 4. See, when the input is negative 89.8, the output is 4.02, and way out here, it's 4.01. But I'm going to go to a table like they said. So I make a table, and then down the left side here, I'm going to put in larger and larger negative values of x. So say starting with negative 10. So you see the value is 4.246 something. Then I'll plug in negative 100. Now it's, the value is 4.024 whatever. Then we'll go negative 1000. Now it's 4.0025. And how about negative 10,000? And then this last one, I'll do negative 100,000, right? Which is not that large, but so you see the larger negative x gets, right? So x is approaching negative infinity. The value of this function looks as though it's approaching the value of 4. And I know in Desmos here, eventually it'll get so close to 4, or whatever its limit is, that it might just say 4 after a while, even though it's not actually going to be equal to 4. It's going to approach 4. But you see, I put in enough of these, like there's negative 100 million. See, after a while, it's so close to 4 that the calculator just says it's, 4. Yeah, it's not 4. It's a little off of 4. And then back on my graph, I'll go back to the default area. If I were to put in the line y equals 4, so you see this like purplish line just show up. I'll make it like a dashed line. So there's my dashed dotted line here, y equals 4. So again, you can see as I approach just the left end, right? Just the left end, the red graph is very, very close to becoming, the purple dotted line. In fact, you zoom out enough, they almost look like they're right on top of each other. All right, and I'll keep going further and further left. Again, the red line, or sorry, the red graph. I'm zooming in, but I mean, see, it's not exactly 4, not quite, but it's, the further left I go, the closer the graph gets to being that line y equals 4. All right, so y equals 4 would be considered a horizontal asymptote. And it's only on the left end, right? You look in the right end, the red graph is getting larger and larger, right? The output's getting larger and larger, going to infinity on the right end. But on the left end, approaching 4. And that's what we're entering. See, it says based on what you see, and they say go to 2 decimal places, right? Plug in large enough stuff so they match the 2 decimal places. And you saw that after a while in the table, see, after I plug in larger and larger values, these start matching the 2 decimal places, 4.00, 4.00, 4.00. So it looks like the limit is, 4.00, which I'm just going to write as 4. And once you've submitted an answer, It'll tell you if you're correct or incorrect, and then give you some sort of answer explanation. I'd highly recommend reading through these, whether you got it right or wrong. If you got it correct, maybe you guessed correctly or you did it in some long, inefficient way, and you read through the answer explanations and see that they're doing it in a much faster way or much more efficient way that you might want to try to use yourself for future questions that are similar. Now, of course, if you got something wrong, I would definitely read through the answer explanation, try to figure out where you went wrong, and hopefully you can learn from your mistake for future questions that are similar. And they got the graph there and everything. Great. All right, so it's switching up. Now it's asking me to determine the limit at infinity, again, either positive infinity or negative infinity, of a rational or other algebraic function. So we're given a function, this one here, where you have a degree 4 polynomial in the numerator and a degree 2 polynomial in the denominator. So remember with polynomials, the highest powered term, the lead term, that'll have a much, if you're plugging in large values of x, the highest powered terms will be much larger than the lower powered terms. So they'll say that those highest powered terms, dominate the polynomial. They have much, much larger values than the other terms. So when you're evaluating a limit at infinity for a rational function like this one is, polynomial over polynomial, you're really only going to have to focus on the highest powered terms. All right, so I'm going to go through and so I'll show you a few things. All right, we'll go through and do this on paper. And I'll explain how I would approach working with algebraic expressions and taking these limits at infinity. So we have f of x equals, this. Now I'm going to put it in descending order. So again, where I write it with the highest powered terms first. So the numerator polynomial has a negative 1x to the fourth term. Then a negative 3x squared term is the next highest power. And then there's a constant term of positive 5. And I would suggest you do the same where you think of your polynomials in descending order like this. And the denominator, the highest powered term, is negative 1x squared. And then the next highest powered term, negative 2x. So we're asked to evaluate these limits, right? The limit as x approaches, so I'll do one at a time here. Positive infinity. So again, this means x is positive. You're plugging in, large values greater than 0 that are getting bigger and bigger. A million, a billion, a trillion, a googolplex, and so on. Of this expression. So my little tip for you is in these algebraic expressions, rationals, and you might see ones with roots later, I'm going to, when taking limits at infinity, again, this is only for when we're doing limits at one of the infinities. All right, so just these here. I'm going to factor out the dominant terms, all right, the highest power on the variable. I'm going to factor out the highest power of x. The highest powers of x, or whatever the variable is, from each polynomial. Right, and factor out the dominant stuff. What dominates each expression? And so from the top polynomial here, I'm going to pull out. So we got the limit as x approaches infinity. So from the numerator polynomial, I'm going to factor out the highest power of x there, which is x to the fourth. Now, if you remove x to the fourth, just for the factor that's left over, just divide every term by x to the fourth, you'd have -1, then -3 over x squared, and then +5, over x to the fourth. So that's from the numerator polynomial. And then in a similar fashion, from the denominator polynomial, factor out the highest power of x, the highest power of my input variable, which is x squared. So I factor x squared out, so now you have x squared times, and then, the remaining factor, again, just go through, divide each term by the thing you factored out, divide by x squared. So I'd have -1, minus, and then 2x over x squared would be 2 over x. And then since x is not 0, right, x is a positive number here, you're plugging in larger and larger positive numbers. We can get some cancellations here, right? X to the fourth divided by x squared. Well, 2 of those factors of x would cancel, and that would leave me with x squared up top there. And so now I have the limit as x approaches infinity of just x squared times, and then this, -1 minus 3 over x squared plus 5 over x to the fourth up top, and the -1 minus 2 over x, down here. Now, in every single one of these fractions, right, the reason we're pulling out the dominant stuff is so you end up with fractions like this, where you have a constant in the numerator, right, -3, +5, -2, and then the denominator, as x goes to positive infinity or negative infinity, the denominators on these, you have -3 over x squared, +5 over x to the fourth, -2 over x. See, what happens is the denominator is getting very large, right? So generally, if you have a constant numerator and the denominator is getting large, all right, large positive, large negative, that kind of an expression will approach 0. It'll get incredibly small, as because the denominator would be getting huge, 3 over a million, 3 over a billion, 3 over a trillion, and that means the whole value of the expression is very small. So the limit, I'm going to write it this way. When you plug in larger and larger values of x, see, x squared would be getting the very, very positive large. I'll put positive infinity for the x squared factor, multiplied by, and then this fraction, the terms of these numerator and denominator in the fraction are approaching -1, right? Remember, constants don't change, -1. But then all these fractions with variables in the denominator, 3 over x squared, 5 over x to the fourth, 2 over x, would be getting very, very tiny and approaching 0. So we got, -0 plus 0 over -1 minus 0. So we have this expression approaching, positive infinity for the x squared factor times, and then -1 over -1, +1. So you have a positive times a positive So this is still approaching, positive infinity. There's my limit. This is an infinite limit, right? It has a limit of infinity. The value of this expression is getting larger and larger and larger positively as you plug in bigger positive numbers. So you don't have a horizontal asymptote on the right end, is what this is saying. So let me actually go to the graph. All right, go back to Desmos. We'll enter this function and do something similar to the first question we saw. So again, I'm going to enter my in descending order. I mean, you could enter it the way they gave it to you too, but negative x to the fourth minus 3x squared, plus 5 divided by, and then my negative x squared minus 2x. And I'll change the color on this. Settings. Make it red or something, right? Some other color, maybe a little thicker even, right? Okay. So look, if I zoom out here, you can look at what happens, to the far right. Going up forever, right? You keep moving to the right, values going up forever. If I make a table, and look at this table, I plug in 10, plug in, now that the output's 85, plug in 100, the output's 9,000, almost 10,000, plug in 1,000, now the output's almost 1,000,000, right? Plug in 10,000. Now, remember this times 10 to the 7th meant move the decimal point to the right 7 places. So this is a very, very large number. All right, that's almost like, it's almost 10 to the 8th. Almost a 1 with 8, almost 1 with 8 zeros after, almost 10 million, or 100 million, sorry, 1 with 8 zeros after it. So the plug in 10,000, the output's almost 100 million. So definitely approaching infinity, and I'll just do one more here just to fill in the table. So if I were to plug in 100,000, that's very, very large, almost 10 to the 10th, almost a 1 with 10 zeros after it, the output there. That's huge. So it looks like as I plug in larger values of x in the positive direction, the output's approaching positive infinity, which again, looking at the graph, if you move to the far right, keep going to the right, the output's getting bigger and bigger and bigger positive. And we'll see the same thing kind of happening here. If I go to the left, okay, nothing would really change. So I'm just going to add to this. Just cross this out here. Let's have x approach negative infinity. So now x is, less than 0. So nothing would change. Right? I'm still doing this. Okay, when we're taking limits at infinity and polynomials are involved anywhere in the expression, I'm going to factor out highest powers. So again, I would pull out x to the fourth from this one, pull out x squared from this one. The cancellation would happen, again, because x is going to negative infinity. It's definitely not 0. So again, negative infinity, negative infinity. And then I'd be left with this expression here. So it's still the same thing, right? X squared. If I plug in larger negative numbers but still square them, I'm getting big positive numbers. So that x squared factor would be going to, positive infinity, large positive. And then this, 3 over x squared, 5 over x to the fourth, 2 over x. Again, all those look like this, where you have a constant in the numerator and some big denominator, big positive or big negative. If that happens, you have a constant numerator and a large denominator. That is a very, very tiny number. That is very close to 0. So that's approaching 0, that's approaching 0, that's approaching 0. So this factor here is once again approaching -1 over -1, which is +1. So positive infinity, something that's positive and large for the x squared factor, multiplied by something getting closer and closer to 1, this fraction factor here. So the limit is still positive infinity. And we can see that. Go back to Desmos. And you look at the graph, if I go to the left forever, maybe I should make this less thick. Go back to 2.5 the way it was. All right, but still, look at the left. Here's a point on the graph. If I go to the left, you see how it's going up, 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 up. The output's still going to, positive infinity on the left end. And if I change my table here, right, instead of plugging in, all positives, I plug in -10, -100, -1,000, -10,000, -100,000. Look at the outputs. They're still, positive 128, positive 10,000, positive 1 million, positive, 100 million, and then, 1 times 10 to the, almost 10 to the 10th again. Very, very large positive outputs. So just looking at these few values from the table here, I would say that the left end behavior, the limit at negative infinity is positive infinity. So I have another infinite limit at negative infinity. You can see it from the graph, from the table, from what I wrote down on paper. So there's no horizontal asymptote, right? This limit at the right, positive infinity, and limit at negative infinity were both infinite, not finite. So no, as you saw in the graph, no horizontal asymptote. But they're just asking us to enter, values here, which will be infinite, right? Positive infinity for both of these. So infinity for the right end and approaching, infinity on the left end. And that's it. I'm pretty sure they don't say anything weird. Yeah, if it's infinite, put infinity. If it's negative infinite, put negative infinity. Great. And read through these, please. All right, they don't have a graph this time. You can always make a graph yourself. Okay. This one's determine the limit at infinity of a rational or other algebraic function. So the last example was a rational function, right? Polynomial over polynomial. Other algebraic means, could have polynomials, rationals, or things involving roots. Those are all algebraic operations. So this one has a root and some polynomials involved as well. All right, so again, I'll do the same thing where we'll try to look at it on paper. And then look at a graph, look at a table, right? You can do all sorts of things to evaluate, estimate what a limit is. So the function I'm given here, again, this algebraic function involving a square root and some polynomial terms, right? You got 3x to the first plus, and then the square root. So remember, this symbol is asking you for the principal square root, the non-negative square root. That'll come into play in a minute. And then inside the root, you got 9x squared, minus 3x. Okay, so just like I did with the last one, I'm doing the limit as x approaches, let's do positive infinity of this expression, 3x plus, the square root of 9x squared minus 3x. So like I did in the last one with the rational function, see this polynomial in here? And there's a polynomial inside this root. Now 3x is also a polynomial term out here, but it's just a single term. So I'm not going to pull anything out of that yet. But from the 9x squared minus 3x, I'm going to factor out the dominant power. I'm going to factor out x squared. So now we have the limit as x approaches infinity of 3x plus, and then if I pull out x squared from that, this becomes the square root of x squared times, and then 9 minus 3 over x. 9 minus 3 over x. Again, I can do that because, again, x is clearly not 0, so we're not worried about dividing by 0 with this 3 over x. X is clearly a positive number. Now, inside the root here, now I have a product. So remember the square root of a product, I can break it up. So this is 3x, I'll write the limit later, plus, and then we have the square root of x squared times the square root of the other factor, this 9 minus 3 over x. Now, hopefully you recall from a previous algebra class or pre-calculus, I'm sure you've seen this sometime before. The square root of x squared. Remember, this is the positive square root, so it's not just x all the time. It's only x if that's actually a non-negative number, right? Your result should be the non-negative square root of the value. So if x is positive or 0, then you can undo them. But remember, the square root of x squared was the opposite of x if x was a negative number, right? Because if x is negative, right, if I wrote just x, that would be the negative square root, but you want the positive square root with this symbol. So to make it positive, right, take the opposite. Now you might have also seen this way, right, where the square root of x squared is the absolute value of x, right? Again, to ensure that you had the non-negative square root, the principal square root. But still, the absolute value of x, remember, the absolute value of a number is either itself, if it's positive, or the opposite of itself, right, if it's negative, right? That'll ensure that you have an absolute value. That'll ensure that you have a positive output. So we're going to keep this in mind when taking these limits at infinity. So here, we're taking the limit as x approaches positive infinity. So again, x is a positive number, meaning the square root of x squared is okay. It's okay to write that as just x. So this is 3x plus, and then the square root of x squared, right? Since x is positive, is just x. And then times, this square root of 9 minus 3 over x. Okay. And now I have these two terms have a common factor, right? They both have this x to the first in common. So I'm going to factor that out as well, right? I mentioned that in the previous problem. Anytime there's a polynomial factor, I'm going to, anytime there are polynomial terms, polynomial factors, I will be pulling out the highest power I see on the variable. Just for these limits at infinity, though. All right, so now I'm factoring out this x to the first from both of these, and we finally have this. The limit as x approaches positive infinity. If I do that, we pull out the x here. That'd be x times, and then 3 plus the square root of 9 minus 3 over x. Okay. So now, as x gets super big, positive, this first factor with just x, that'd be going to positive infinity. That'd be getting gigantic, very large and positive. Multiplied by, and then this other expression, the other factor would be, 3 will stay 3. Remember this 3 over x, where you have a constant numerator and a denominator that's getting large? That's going to 0. So this other factor is approaching 3 plus the square root of 9. Well, the square root of 9 is 3, so this other factor is approaching 6. So we have first factor getting large positive, approaching positive infinity, and this second factor is approaching the value of 6, positive 6. Well, if you take a positive large number and multiply it by a positive, it is still positive and large. So our limit is positive infinity. Now, we can see that in a graph in a table. Right? I'm going to punch this function in. Go back here, Desmos. So here is the function we were given, right? F of x equals 3x plus, and then square root of, and then inside the square root 9x squared minus 3x. Right? So if you see on the right end, zoom out a bit, the graph is going up forever, right? Getting larger and larger and larger as you go to the far right. Right? Has no limit, or an infinite limit. And if I make a table, plug in larger positive values, 10, 100, 1,000. Right? Just keep throwing zeros on this. 10,000, 100,000, and so on. Right? There's a million. Right? I see the bigger I make that number, the larger the output is. This is 6 with 9 zeros after it, right? 6 billion when I plug in 1 billion. Right, this I'll go back to the 100,000 there. But you see, as x gets larger, positive, right? So the limit at positive infinity, the output is getting larger and positive as well. And you can see that clearly in the graph too, right? Getting big positive to the right. So my limit at the right end, I'll say, is infinite positive infinity. But if you notice, see, the left end is not doing that. See the graph on the left, it looks like it's approaching like a half. Go to the far left here. See how the outputs are 0.49 something, 0.498, 0.499. It looks like it's approaching a half on the left end. And if we look at our table, bring that back, make all these negative, plug in negative 10, negative 100, negative 1,000, negative 10,000, negative 100,000. Look at these outputs. 0.49, 0.499, 0.4999, 0.499. It looks as though the limit is a half, 0.5. It's getting as close to 0.5 as you want. Now, back here, if I were to do this again, and take the limit as x approaches, negative infinity. So something not so nice is going to happen this time. Right? So again, I would do all the same stuff. Now x is, negative. And because x is negative, right, because x is negative this time, this square root of x squared I had would be the opposite of x to make it the positive root. So now I have this negative x here instead of plus negative x, and then I would factor out an x, and now instead of x times 3 plus the square root of 9 minus 3 over x, it's now, so the limit as x approaches negative infinity, it's now x times the quantity 3 minus the square root of 9 minus 3 over x. So this first factor is approaching positive infinity. This second factor is approaching 3 minus 3, which is 0. And this is bad. So again, this is referred to as an indeterminate form. And we'll talk more about indeterminate forms for limits in section 4.8 on L'Hopital's rule. But yeah, infinity times 0. So again, something approaching infinity, something getting larger, positive, larger, negative. And this is something approaching 0, right? This is 9 minus 3 over x here. This isn't just 9. So it's 9 minus, something tiny. So this value is approaching 0. It's not actually 0. If it was actually equal to 0, then the value would be 0. But this one factor approaching infinity, again, positive or negative infinity, multiplied by, and then another factor approaching 0, getting closer and closer to 0 without actually being 0. Once again, this is indeterminate. You cannot tell me what the limit is in that form. So instead, all right, so I do all that, what I normally would do with polynomials and be like, oops, something bad happens. I can't tell you what infinity times something close to 0 is, something large times something small. I can't tell you what that's going to be. So then we have to approach this limit another way if we're going to do it by hand. So I'm going to take this here, 3x plus, square root of 9x squared minus 3x, and think of it as a fraction. All right, put it over 1. So remember some other thing. We've seen indeterminate forms before, back when we were introduced to the first derivative and limits of ratios. Other indeterminate forms were, when the numerator and denominator are both approaching 0, or when the numerator and denominator are both getting large, positive or negative infinity. In those cases, you had to manipulate the expression somehow. So again, here's another indeterminate form for you. Infinity times something getting close to 0. So we got to manipulate this expression if we're going to do this by hand. Now I know I said the limit was a half. Right? We saw the limit looks like it's a half from the graph and from the table. But remember what we did when we tried to retool an expression involving a root when we had an indeterminate limit before? Multiply by its conjugate. So the conjugate of this would be 3x minus the square root of 9x squared minus 3x, right? Just change the sign in the middle for the conjugate. But I also multiply the denominator by this, right? 3x minus the square root of 9x squared minus 3x. So this is the same expression as the initial. Now, multiplying conjugates, you get a difference of squares. 3x times 3x, that would be 9x squared. And then minus, and then this square root squared would be the radicand, right? Minus this 9x squared minus 3x inside. And then I distribute the negative to this, right? So my numerator, 9x squared minus 9x squared, would be gone. And then minus negative 3x, the numerator simplifies to just 3x now. And the denominator is this conjugate thing. And then in the denominator, I would do all that same stuff I did on the previous page. I would do factoring out the x squared from the 9x squared minus 3x, then the square root of x squared. So again, we're taking the limit as x approaches negative infinity now. So again, I'd factor out the x squared from this. I'm not going to write all this again. And then I'd have the square root of x squared, which, because x is negative, would be negative x. So I'd have down here 3x minus negative x, so plus x, times the square root of 9 minus 3 over x. And then I factor out x from this, right? From these both have polynomial factors. Factor out x from this, and we get the following. You got 3x in the numerator, and then x times, and then 3 plus the square root of 9 minus 3 over x. And now since, again, since x is not 0, right, x is approaching negative infinity, so clearly not 0, these will cancel. And now we're taking the following, right? Now we have, sorry, I should be writing the limit every time, but so now we're taking the limit as x approaches negative infinity of this expression, 3 in the numerator over, and then 3 plus the square root of 9 minus 3 over x. So you see how the numerator is a constant. All right, so these are going to approach 3 in the numerator, and then just like before, this 3 over x expression here would be going to 0. So the denominator is approaching 3 plus the square root of 9. So 3 in the numerator, 3 plus 3, 6 in the denominator, and I reduce that to a half, right? There's the limit as x goes to negative infinity. And so, that is finite. So y equals a half would be considered a horizontal asymptote, right? If I were to go back to Desmos here, put in y equals 1/2. I'll change the color up so they contrast a little more. Dotted in. You see how the graph on the left approaches this red line, gets closer and closer to y equals a half. I'm zooming in right now, but you see how this is the graph of my function, and you see as I move to the left, getting closer and closer to the line y equals a half, right? That's what the red dotted line is. Zoom out a bit more so you can see how they're they're so close, they almost look like they're on top of each other, but they're not, right? Again, the value is a little under a half on the blue graph, right? Just barely underneath. Right. So left side limit, 1/2, positive 1/2. And submit. Great. So again, the hand, doing all this multiplying by conjugate stuff, you might not think to do that initially, but if you end up with an indeterminate form, again, so now we have 3 of them. 0 divided by 0, some kind of infinity over infinity, and now we have some kind of infinity times 0. These are, again, referred to as indeterminate limits, indeterminate forms for limits. So if you see those, you come across those, you have to go back and retool the expression somehow so that you can apply the limit laws and find limits. Or you can do what I was doing initially with this limit at negative infinity. Look at the graph of the function, make a table, and you can probably guess quite often. You can probably guess what the limit is looking at a table, looking at a graph. Right. Not always. Sometimes maybe if the limit were 7 pi over 3, you probably wouldn't be able to tell what that was just by looking at a table. You'd have to manipulate and do it by hand. But quite often in these problems initially, you should probably be able to tell what the limit is by looking at a table or looking at a graph. All right, so now we're given oblique. This objective is find oblique asymptotes of a function. So let me explain what that is real quick. So oblique asymptotes. These are just linear asymptotes, so graphs of lines that the original function will be approaching on the ends that aren't horizontal. So these are linear asymptotes that are not horizontal. Well, that are not vertical or horizontal, right? Vertical asymptotes can't be touched, right? That's where you have values that are not in the domain at vertical asymptotes. So that are not vertical or horizontal. Right, so they have the form, y equals mx plus b, where m is not 0. So when you're looking at a graph, so an oblique asymptote, so here's one with a positive slope, right, some dashed line. So yeah, if a graph is, approaching this, so I could have something like this where the graph is approaching this on one end, maybe on the other end as well. It doesn't have to approach on both ends, right? Remember, as long as it's doing it on one end, it's still considered an asymptote. Make that a little darker. This marker's had it. So again, this should be considered an oblique asymptote. Now, in rational functions, which is what we have in this next problem, so that's where you have y equals, f of x equals a polynomial in the numerator, polynomial in the denominator, polynomial divided by polynomial. When the degree of the numerator is one larger, right, one more than the degree of the denominator, then there will be one of these oblique asymptotes. In fact, when you have a rational function, then you got, polynomial, say numerator polynomial n of x divided by denominator polynomial d of x. So n of x over d of x, numerator over denominator. If you were to actually divide, you'd get some quotient q of x plus, and then some remainder divided by the divisor, right? Remainder over denominator. This is going to approach 0, goes to 0 as x gets large, because this is going to have a numerator with a smaller degree than the denominator. So the quotient is going to be this oblique asymptote. The graph of a rational function, say y equals f of x, where again this is rational, will approach y equals q of x, right? The quotient when you divide the numerator by the denominator as x goes to positive or negative infinity. The graph will approach the quotient of the division on both ends. All right, so we'll see that here. All right, so in this one, we do have that case where the degree of the numerator is one more than the degree of the denominator. So f of x equals, x squared minus 2x minus 1 over, negative x plus 1. And we're asked to do this. It's one of those interactive problems, right? On the graph below, move the 2 points to graph the oblique asymptote, right? So you got this red dotted line, right? That the graph, you see this black graph, the graph of the function needs to approach on both ends, get closer and closer to on both ends. We just need to determine, points on that line. So we got to figure out the quotient when dividing these. So I'm going to do some polynomial long division. Hopefully this rings a bell from some pre-calc or algebra class you've taken before. I'm assuming that you have done polynomial long division before if you're at this point in your mathematical career. So numerator x squared minus 2x minus 1, and this is being divided by negative x plus 1. Now you could multiply the top and bottom by -1 and do synthetic division, but I'm going to go into law division here. So law division symbol, got the numerator polynomial inside, right? The dividend, denominator polynomial outside here, the divisor. So our first step is to divide the lead terms. X squared divided by -x would be -1x, and that'll go up here in the quotient area. And then this gets multiplied by the denominator, the divisor. Write that under here. -x times -x is x squared. -x times 1 is -x, and I'm lining up like terms. And then we subtract, right? It's division, multiplication, subtraction, just like dividing with law and division for whole numbers. Same steps. And then if I subtract these, x squared minus x squared is nothing. -2x minus -x, that'll be -2x plus x, it'll be -1x. And then, -1 minus nothing is -1, kind of like drop that unused term down. And then after subtraction, take a look at the degree again. This is degree 1. The divisor, the denominator is degree 1. You keep going, you keep repeating these steps until the degree after subtraction is smaller than the degree of the divisor. So that's not happening here. So I start over. Divide the lead terms. -x divided by -x is +1. That goes up in the quotient. Then I take the term I just wrote in the quotient, multiply it by the divisor, that'd be -x plus 1, put that here, subtract from the line above it, and the x's are gone, and the -1 minus 1 is -2. And this would be, now that's degree 0, degree 1, we're good. So this is the quotient. All right, if I were to rewrite this fraction out, I could write it as -x plus 1, and then, -2, that's the remainder, -2, -2 over -x plus 1. These have the same value, no matter what you plug in, as long as you're not plugging in 1, right? This would have a vertical asymptote at x equals 1, because, not defined there. Yeah, so like I said, this term here, where the numerator is the remainder and the denominator is, the denominator, this would approach 0 as x gets large, right? Because the numerator's 2 and the denominator would be getting gigantic, right? So this is shrinking. So yeah, the quotient, y equals the quotient, will be our asymptote. And since it's a linear function, they call that an oblique asymptote. So this is our oblique asymptote for this graph. Now let's take a look at the graph in Desmos before I go and manipulate the question. All right, so back in Desmos, back to home here. So here was the function we were given. It was numerator polynomial was x squared minus 2x minus 1. Denominator was just -x plus 1. Now I told you, here's I'll call this q of x because it's the quotient. Oh, you know what? No. I'm going to rewrite that with the division. So I'll go y equals, remember when you divide those two, I end up with -x plus 1, plus 1. And then I said remainder was -2 over, -x plus 1. And you see how the graph I just put up is the same as the original. I'll turn it off and on, right? This is the result of the division of these two polynomials. Quotient plus remainder over divisor. And you see how they are the same function, same graph. So look, when I put in just the quotient though, y equals -x plus 1, and I'll make this a dashed line. This is going to be our oblique asymptote. So look at the graph. See how to the far right, graph is approaching this red dotted line. To the far left, and the graph is approaching, getting closer to this red dotted line. If you zoom out enough, that red dotted line, looks like it's right on top of the graph. Right? If you zoom out enough, they almost look like they're the same, even though when you zoom in, they're not exactly the same. Right, if I zoom in a little more here, but still, the graph on the far left approaching this line, right? and the graph on the far right approaching this line, right? So this linear asymptote, again, that's not horizontal, it's not vertical, called an oblique asymptote. So what I want to do now, back on the problem, is move my points so that, I mean, two easy points would be the intercepts, right? 0, 1, and 1, 0. I'll just move my points to those. So back on the problem, I'll just move one of these points to 0, 1, and the other one to 1, 0. And there, that should be good, right? And see how that picture looks like this one. Kind of maybe match them up yourself. And that should be good enough. Great. So again, they take you through the answer explanations and all that, do law and division, remind you how to work that out. Great. All right, so back to limit at infinity. This is another one where, we're just given a graph. So can you tell from the graph what the limits at infinity are? So here for the function f of x, whose graph is shown below in blue, all right, find the limit as x approaches, positive infinity. It says you may zoom in, explore the graph. It's just, this is through Desmos here actually. But if you see, if I go to the far right, look at these outputs, 2.5, 2.4, 2.3, 2.2, 2.1, 2. You can move over, 2.0, 9, 08, 07, 06. And even if you were to look at, I don't know, it looks to me as though the outputs as I move to the far right are approaching the value of 2, getting closer to the line y equals 2. I know y equals 2 isn't in there, but it looks as though the outputs are getting as close to 2 as you want it to get, right? 2.04, move further right, here's 2.03, 2.02, it looks like the outputs are approaching 2 to the far right. And that is, I think that's all they want, right? So the limit as x approaches infinity, positive infinity looks like 2. Even if they ask for negative infinity, that still looks like it's 2, right? Getting closer and closer to y equals 2 on the far left. So either way they sliced it, looks like the limit is 2. And they actually put the dotted line y equals 2, the horizontal asymptote, in the answer explanation graph. All right, so now for polynomial functions. Again, polynomials should be simple enough. Now, polynomials don't have horizontal asymptotes. So these limits at infinity are either going to be infinite or negative infinite. They'll be going up forever or down forever. Now, you may recall some polynomial end behavior, from pre-calc or some algebra class you've taken before. So like, look at this polynomial here. Got, x to the fourth, it's an even degree, and got a negatively coefficient, right? So no matter what infinity I'm going to, plug in a million, a billion, a trillion, or negative a million, negative a billion, negative a trillion, it's being raised to the fourth power. So that x to the fourth is going to be a large positive number, but then it's getting multiplied by -3, right? So a positive times a negative. This is going to be a large negative number on both ends. And if you were to look at the graph, right, here's, f of x equals -3x to the fourth. You see how the graph, the output to the far right, to the far left, you could make a table, plug in big positives, big negatives, the output is going, down forever, right? The output's going to negative infinity. And you may recall that, right? Even degree, negatively coefficient, the graph was going down forever for a polynomial function on both ends. So the limit at either infinity is negative infinity, right? So I'm just putting negative infinity in for both of these. Real simple. Look at a graph, make a table, or just think about it. You should be able to figure that out. All right, now for a transcendental function. So again, horizontal asymptotes, limits at infinity. If they approach some finite value, you get a horizontal asymptote. It's approaching some horizontal line. A lot of these trig functions, right? Now, transcendental could be trig, inverse trig, logs, exponentials, right? Just not algebraic. So here's one involving cosine. And just think about what would happen here if x got large. And I'm still going to go to I'll go to a graph, I'll go to a table. We'll do all the same stuff I've been doing with all the other problems. But let's think about it on paper first. So my function, 7 times the cosine of, and then inside that cosine is 1 divided by 7 minus 9x. So this expression inside here, I hope it makes sense that as x gets large, it goes to positive or negative infinity. This is one of those fractions where the numerator is a constant. The denominator would be getting gigantic. All right, negative 9 million, negative 9 billion. The plus 7 won't mean too much when the number here is large. But 1 over negative 9 million, 1 over negative 9 billion, 9 trillion, whatever, is getting very, very small. So the limit on either side, as x goes to positive or negative infinity of this function, should be approaching 7 times the cosine of 0. And the cosine of 0, remember, is 1. So we got 7. Our limit looks like it's going to be 7. Y equals 7 will be the horizontal asymptote for this. Now, I'm still going to go look at the graph, make a table. All right. Make sure you're in radian mode, by the way. Have radians, not degrees, for your trig function. So we have f of x equals 7 times the cosine of 1 over 7 minus 9x. And you see, I'll put in the graph y equals 7. Maybe make it a dashed line or something. And you can see that, it basically looks like it's right on top of the graph that we made. All right, turn this off and on. It's to the far right and far left. They're so close, they look like they're right on top of each other. But if you zoom in close enough, right, let me just go over here. Yeah. See, they're not the same though, right? You zoom in close enough, that red graph is not the same as the blue graph. It's just getting closer and closer to 7 on the far left. And also, closer and closer to y equals 7 on the far right. And if you were to make a table and do the table thing for the function, you can plug in 10, 100, 1,000. Look at that. Even after 1,000, it eventually is so close to 7, just says it's 7. It's not actually 7, but it's so close to 7, just says 7. The same thing for your negatives, right? Plug in negative 10, negative 100, negative 1,000. Again, it's so close to 7, it says it's 7. So both limits are 7. Wonderful. All right, so another one with the oblique asymptotes. Just what would be, remember the rational functions where the degree of the numerator is 1 higher than the degree of the denominator. You're going to have one of these oblique asymptotes. Now let's just find the equation for the oblique asymptote. So basically, what's the quotient? Remember, the graph will approach the quotient for these on the ends. So here y equals x squared plus 1 divided by x minus 1. And you can do synthetic division if you wish, because that's a linear divisor with a coefficient of 1, lead coefficient of 1. But still, I'm going to do this x squared plus 1 in here, x minus 1 out here. So the lead terms divide to be x. multiply these, you get x squared minus x, and then subtract this from the line above it. Now the x squareds would go, now there's no x up here, minus negative x, so there'll be positive 1x down here. 1 minus nothing is 1. And then divide the lead terms once more, that's plus 1. And then you get x minus 1, subtract these, you got a remainder of 2, right? So this is x plus 1 plus, and then 2 over x minus 1. These are the same thing. The quotient, though, right, and this remainder over denominator factor term will approach 0 on the ends. So you'll be getting closer and closer to this quotient line. All right, so y equals x plus 1. Again, they'll be calling that our oblique asymptote. And that's all I'm entering. Now you could go make a graph of this and the graph of y equals x plus 1 and see how on both ends the graph of this function will get closer and closer to the graph of the line y equals x plus 1, but I'm just going to enter it now. I've already done a bunch of these. Great. And there's the graph that you would be seeing. Right, so another one. Now this is your inverse cotangent. So remember, either way, look at the lead term of the polynomial in here is 4x squared. So whether x gets huge positive or huge negative, the expression inside here is going to be huge positive, right? And you might recall, okay, so if you remember your inverse trig functions at all, so again, the function we're given here is 8, times the inverse cotangent of 5x plus 4x squared. So yeah, this would be approaching infinity as x goes to positive or negative infinity, right? This is a polynomial with a degree 2 positively coefficient, so it's getting large positive on both ends. But so this limit, as x approaches, either positive or negative infinity of this function, will be approaching 8 times whatever the inverse cotangent of a infinity is. Right, because again, this interior expression is getting large positive. Remember the graph of inverse cotangent? That was between, y equals 0 and y equals pi. And, inverse cotangent of 1 was pi over 4, and inverse cotangent of 0 was pi over 2, and -1 was 3 pi over 4, and blah, blah, blah. And you had these, asymptotes of 0 and 1. This is your inverse cotangent. And it was something like this. Looks something like that. All right, that was your inverse cotangent function. So as you go to the far right, inverse cotangent is approaching 0. So this is equal to 8 times 0, which is 0. All right, so the limit should be 0 on both ends, again, because that interior expression is going to positive infinity on both ends, getting larger and larger positive values in here, and the inverse cotangent of a larger and larger positive number is getting smaller and smaller, going to 0. But once again, just to double check myself, let's enter this. So f of x equals, now I'm going to put arctangent, 8 times the arc cotangent, right? Inverse arctangent, sorry, arc cotangent, inverse cotangent of, and then 5x plus 4x squared. Go back to home here, and you see on the far right going toward the x-axis, far left going toward the x-axis, right? The y values are going to 0 on the right, going to 0 on the left. And you can make a table if you wanted, but the limit on both ends here is 0. So 0 for both of those. Right, I don't know if they have a graph or anything, but they do a table. I don't know why they put in degrees in here. Should be doing entering radians, but whatever. All right. Great. I mean, either way, radians or degrees, you end up with lower and lower values. All right, so now the polynomial function. So again, you just got to determine the lead term here. Now, if you were to multiply all the lead terms, 3x squared times x squared would be 3x to the fourth, times x would be 3x to the fifth, and then you got this minus out here. So the lead term of this polynomial would be negative 3x to the fifth. So it's got odd degree, negative lead coefficient. So on the right end, it'd be going down forever. So the right limit, the limit at positive infinity, would be negative infinity. And on the left end, it'd be going up forever. All right, so the limit at negative infinity would be positive infinity. Again, focus on finding the lead term of a polynomial. That'd be, again, negative 3x to the fifth, odd degree, negative lead coefficient. Be going up forever on the left, down forever on the right. All right. They do the table thing. You can look at a graph. All right, so once again, looking at a graph here. Now this is an interactive one. So it says on the graph of the function f shown below in blue, choose whether there are 0, 1, or 2 horizontal asymptotes by adjusting the red horizontal slider button on the upper left-hand corner of the graphing window. Then graph any asymptotes using the provided green dotted lines by vertically dragging the orange points. So look, they got two asymptotes here, right? There's two of these green dotted lines. So, actually, look at the blue graph. See on the far right, looks like we're approaching a value of, well, I guess can't zoom or anything, but it looks like there's an asymptote. It's approaching some positive value, maybe a little bit more, a little under 1.3. So I'm approaching some positive value on the right end, and then approaching some negative value, like negative 2.7, 2.8 on the left end. So you're approaching different values on the end. So it looks like two different vertical asymptotes here. So they got the two asymptotes in. So I'm seeing now, see if I change this to 1, it's only going to give me one dotted line to move. And if I change it to none, then there'll be no dotted lines. But again, because the graph is approaching, some positive value on the left, that's not infinity, and some negative value on the right, on the left. Sorry, I said on the left earlier. Is approaching some positive value on the right and approaching some negative value on the left. Two different values it looks like it's approaching that aren't infinite. So I'm going to move this red dot to the two asymptotes, and then we're moving the yellow dot here. Just move it to right, just to where it's right underneath there. So it looks like it's approaching this y equals 1 line on the right, and then like this, see how I look, y equals -3. I move the green dotted lines so that they look like, the blue graph is approaching them on the ends. So it looks like, just from the picture, that y equals 1 and y equals -3 are the two, horizontal asymptotes for this particular function. Great. All right. And then here's one like way back with the first question, where they're asking us to use a calculator and to see what, try to guess what the limit as x approaches infinity is for this function here. So negative, square root of 3 times x plus, and then the square root of 3x squared plus 1, and then -2. I'm going to go do what we did in the first question of the video, and we'll make a table for this, see what happens as we plug in larger and larger values of x. So this function that we're given, f of x equals, it was negative square root of 3, and then times x outside of that, then plus the square root of 3, I think it was 3x squared, and what? plus 1 and then minus 2. Plus 1 inside, then minus 2 outside. All right, so now notice the limit at negative infinity looks like it's infinity, but they're asking us for the limit at infinity, right? So to the far right. Now I'm going to guess it's negative 2 just based on this. So if I go to the far right here, negative 1.97, negative 1.98, negative 1.99. Looks like it's negative 2. I'll make a table though. Again, we'll plug in larger and larger values of infinity. I'm just going to do it on this top line here. So I plug in 10, negative 1.97. Plug in 100, negative 1.997. Plug in 1,000, negative 1.9997, and so on. Right? It looks like eventually it'll be so close to negative 2, it's just going to tell me negative 2, right? There, right? So it looks like the limit is negative 2. So this limit as x approaches positive infinity, negative 2. Wonderful. All right, so that one's done with the just plugging in tables and whatnot. There's the graph again. Okay. So another polynomial function once again with the polynomials. Just what's the lead term, which there's only one term here. Now it's got even degree and a negative lead coefficient. So those kinds of polynomials go down forever on both ends. So the limit at both infinities is negative infinity. So I'm just putting negative infinity for both of these and submitting. Real quick and easy. Another polynomial one. Now this one has just a single term once more. So the lead term is, 16x to the fifth. Now this has an odd degree and a positive lead coefficient. Right? So as x goes to negative infinity, this would go to negative infinity as well. And as x goes to positive infinity, this would go to positive infinity as well. So down forever to the left, up forever to the right. So my right limit, the limit as x goes to positive infinity, just positive infinity. And negative infinity would be negative infinity. And it's, again, very simple. The polynomial ones, hopefully. All right, so that one's done now. All right, so now the algebraic ones. All right, so remember I can make a graph here, or look at the lead terms. You have the square root of 2x to the 8th. 2x to the 8th would be the highest power up here. Now that'd be the square root of 2 times, now the square root of x to the 8th will be x to the 4th, no matter what x is, because x to the 4th, whether you're positive or negative for x to the 4th is positive. So the square root of x to the 8th is just x to the 4th, not going to be the opposite of x to the 4th. And then, highest powered term down here is negative 3x to the 4th. The x to the 4ths would cancel, and it'd end up with, positive square root of 2 over negative 3. So the limit on both ends is going to be negative square root of 2. Well, I can't just do that. It's not Desmos. Divided by 3 on both ends, and we'll see that. I'll make a graph. So this is one of those where you probably wouldn't be able to say what it was just from a table. But both of these will be negative square root of 2 divided by 3. All right, so watch. Let's go punch this in. So we have the square root of 2x to the 8th with plus 3 inside, divided by, and then negative 3x to the 4th, plus x. Now, you see how it definitely has a horizontal asymptote, and this looks like it's approaching this same negative 0.47 value on both ends. See how it's going to negative 0.47 something over here, going to negative 0.47 something over here. So again, negative square root of 2 divided by 3 is that negative 0.47 something that I said you'd be approaching. All right. And again, it's the same on both ends because the square root of x to the 8th is, just x to the 4th, not positive x to the 4th on one side, negative x to the 4th on the other, because x to the 4th will always be a positive value. You'll always have the positive square root no matter what x is up here. Just gotta be careful with that with the roots. So yeah, that's it. Negative root 2 over 3. I don't think they said enter an exact answer, right? No rounding, so that's it. Should be good. And they go through explaining that all here. Great. This is very much the same thing, right? Notice it's got square root of x to the 8th when in the lead term. So that'd be x to the 4th once again. Don't worry about being, that's always a positive number. So that'll always give you the positive root. So, and then you got negative 2x to the 4th down here. The x to the 4th would cancel when I'm focusing on the lead term. So the limit on both ends would be positive square root of 5 divided by negative 2. So negative, square root of 5 and divided by 2 outside of that, right? And same thing here. Both ends, same. Very similar to the last one. All right, great. So that one's done. Again, oblique asymptotes. Now it says, which of the following functions will have an oblique asymptote? So it's just a multiple choice thing. And you should remember, you're going to have an oblique asymptote when the degree, and for these rational functions, when the degree of the numerator is one more, just one more, than the degree of the denominator. So this would be, if you multiply it out, would be a degree 2 over degree 2. So no, degree 2 over degree 2, no, degree 2 over degree 1, it's this one. And then degree 1 over degree 2. Again, this one has numerator with degree 2, denominator with degree 1. The degree of the numerator is 1 larger than the degree of the denominator. So the quotient would be a linear function. The graph would be approaching some non-horizontal line, right? This oblique asymptote on both ends. Okay. And then another one where it says select all. This one, there could be multiple answers. The functions that will have an oblique asymptote. So once again, where the degree of the numerator is 1 larger than the degree of the denominator. So this one, right, degree 2 over degree 1. This is not degree 1 over 2. This is 2 over 1, so this one also would have an oblique asymptote. And this is 2 over 2, so no, just F and H here would have an oblique asymptote. Right, so that one's good. All right, so this one's a little different. So I'll show you how you'd be using properties of logs here, because if you let x go to infinity, this would be the natural log of infinity minus the natural log of infinity, which would be infinite minus infinite. Now that is another one of these indeterminate forms. So we have 0 divided by 0, infinity divided by infinity. We saw infinity times 0 earlier. That's also bad. So here we have f of x equals, the natural log of 5x squared minus 5 minus the natural log of 8x squared, minus 6. And we're taking the limit. They're asking us for the limit as x approaches positive infinity of this expression. Now, if I left it the way it looks, if I just left it this way and thought about what happened to the expression as x got large, again, this expression inside this log would be getting very large. And so remember, the natural log of a large number is also large. So this would be going to infinity. Then we got minus, and then the same thing here, right? 8x squared minus 6 would be getting bigger positive. And so the natural log of that would also be getting bigger. bigger positive. So we have a positive infinity minus another positive infinity. Infinity minus infinity. Don't say this is 0. All right, this is not good. This is another one where it's considered indeterminate. And we'll, like I said, I said this earlier in the video, but talk a lot more about these indeterminate limits, indeterminate forms of limits in the next video or a couple videos from now on a section on or an assignment on something called L'Hopital's rule. We'll be talking a lot more about indeterminate forms of limits in that video. This is another indeterminate form, infinite, where you have a sum or a difference, and one term is going to infinity, the other term is going to negative infinity. You have infinity minus infinity. You cannot say what this is right now. And again, don't say it's 0. These are not actually numbers, right? This could be going to infinity faster than that one, or this could be going to infinity faster than that one, or they could be going at a rate of 1 to 2 or whatever, at the same rate or something like that, whatever. Just know that if you have an infinite term minus another infinitely large term, you can't say what that limit is. All right, another indeterminate form. So we have to manipulate the expression. Now I'm going to use properties of logarithms here. Remember when you subtract two logs with the same base, you can put them together as a log of a quotient, a fraction. So this is equivalent to the natural log of 5x squared minus 5 divided by 8x squared minus 6. And now, if I look at it this way, when x approaches infinity, this expression in here would approach 5/8, right? Just look at the lead terms of these polynomials. X squareds would go, this would be approaching 5/8. So now I see my limit is whatever the natural log of 5/8 is. That's the limit. And I'll show you that in a graph again. All right, let's go to a graph. So here was the function the way that it was originally given, right? F of x equals the natural log of 5x squared minus 5, then minus the natural log of 8x squared minus 6. All right, so you see how to the far right, definitely approaching some value, this negative 0.471 value, negative 0.47 something. And then the same thing to the far left. The graph is approaching this, negative 0.47 something. Now, it didn't say round, right? It said give an exact value. And I told you it was going to be the natural log of 5/8, which you see that is negative 0.47 something. And if you make a table, I'll make a table for this. Let's plug in bigger and bigger positive values, 10, 100, 1,000, a million. See, it's approaching this negative 0.4700363. That's this, rounded to so many decimal places, right? That's this value, this natural log of 5/8. So again, enter an exact value. Now, if the limit didn't exist, we'd put the empty cent symbol where it's not approaching anything. But it is natural log. Oh, did it say round? No, it didn't say anything about that. So just natural log of 5/8. Didn't say anything about rounding. There we go. That should be good. Right. All right, and this one has exponentials. So again, I'll talk about these. What happens now? Remember exponentials. If you take a base bigger than 1, like e, raise it to a negative power, a negative large power, remember that's going to 0. All right, so let's write all that out. So this time, given function involving exponentials, so numerator we have negative 5 plus 2 times e to the negative x. and over 5e to the negative x plus 6. Now, as x goes to positive infinity, remember e to the negative x, remember that's equal to 1 over e to the x, right? Something to a negative power. So that would be going to 0, right? The numerator is 1, the denominator would be getting gigantic, e to the million, e to the billion, e to the trillion. And then as x goes to negative infinity, e to the negative x will be going to infinity, right? Because again, you plug in the power up here is the opposite of x. So if I plug in negative a million, that'll be e to the million. If I plug in negative a billion, that'll be e to the billion, right? So that'll be getting huge. But e to the x would be going to 0. If you plug in negative numbers, e to the negative million, e to the negative billion, e to the trillion, we're going to make use of that. So the limit as x approaches infinity of this function. So if I have x going to infinity, as x approaches infinity, again, these e to the negative x, as we saw, will go to 0. All right. So this would go to 0, this would go to 0. So we end up with negative 5/6 for the right side limit. But then the limit as x approaches negative infinity, well, now that's a problem. Because now the numerator would be going to infinity, the denominator would be going to infinity, right? Because again, you plug in big negative numbers, this e to the negative x is getting huge. This e to the negative x is getting huge. So you got infinity over infinity. Remember, this is one of those indeterminate forms again. I can't tell you what this is, infinity over infinity. So that's no good. So I got to retool this. And the reason I wrote this part is because something I can do is multiply the top and bottom by e to the x. And that turns the top into negative 5 e to the x plus 2. And the bottom, when I distribute, same thing down here. And the bottom into 5 plus 6 e to the x. Now if I look at it this way, when x goes to negative infinity, this negative 5 e to the x would go to 0. This 6 e to the x would go to 0, and I'd be left with 2/5. 2 in the numerator, 5 in the denominator. So this is one of those functions that's going to have 2 horizontal asymptotes. We'll see that in the graph. I'll show you in the graph. F of x equals, now the numerator, right, was this negative 5 times e, or sorry, negative 5, well, I'll just put it the way they originally had it, plus 2 times e to the negative x power, or opposite of x power, divided by 5e to the opposite of x to the 6. So look, I mean, I know I change the color on that so it doesn't blend with the axes. So you see the far right, we're approaching some negative value, right? Negative 0.833 something. And then to the far left, approaching some positive value, which is getting closer and closer to 0.4. It looks like 0.399, or 0.4 is 2/5. Right? If I go y equals 2/5, what we said was our left limit, and our right limit we said was y equals negative 5/6. I'll change these up, make them like green and dotted. I like the dash better. All right, so you see on the far right, graph's approaching the line, you know, y equals 2/5. Right, if I turn that off and on, you see how it's right on top of that almost. And then on the far left, approaching 2/5, and then you see on the far right here, it's getting closer and closer to this, you know, y equals negative 5/6 line, the 0.833 forever, negative 0.83 forever. So those, and you can go to table, make a table if you want, but those look like my correct limits. So as x approaches positive infinity, the limit is negative 5/6. And as x approaches negative infinity, the limit was positive 2/5. Okay. All right, and this one had a trig function. All right, now this is not inverse cosecant. This is just cosecant. So remember how cosecant and remember how all your trig functions oscillate? They all not oscillate, but they keep repeating themselves over and over again. They have a period and keep repeating as that period goes on. Now 6x squared's in here. So when x goes to infinity or negative infinity, the value inside is going to get large and positive. So we're going to see what happens to cosecant for large positive inputs. But you're going to see that's not going to approach a specific value. It's not going to be always going up forever or always going down forever or approaching some horizontal line. All right, let's take a look. So again, I'm in radian mode. We got f of x equals 4 times, it was the cosecant of 6x squared. Now look at this. Look at this nastiness. All right. This isn't doing anything in particular here. See, as you go to the far, ew, yikes. As you go to the far right, this is not good. Look at all that green. The graph to the far right is not approaching anything in particular, right? You're not going up forever. You're not going down forever. You're not approaching some horizontal line. So this limit doesn't exist. The graph to the far right, not approach. I zoom out long enough, it'll look like it takes up the whole thing. I mean, it doesn't take up the whole space. I mean, if you zoom in close enough, you're going to see some gaps, right? But to the far right, to the far left, this graph is not approaching anything in particular. Not going up forever, not going down forever, not approaching some horizontal line. Nothing specific is happening on the ends. So because of that, they would say these limits don't exist, right? You're not approaching infinity, you're not approaching negative infinity, you're not approaching 2 or some finite value. So if that's the case, right, this is one of those ones where you're entering this circle with the slash symbol and the empty set symbol, right, to indicate that the limit doesn't exist. All right, cool. All right, so those are all the objectives on that first heading. All right, the limits at infinity. So now comes the sketch the graph of a function. It says without using a graphing calculator. So I'll go through what you would normally do to try to sketch these things without a graphing calculator. So I'll just go through this one example and the steps I'd go through trying to determine, how to graph this by hand relatively nicely. And then we'll come back here and then they just have choices, right? So choice 1, choice 2, choice 3, choice 4, just which of these is the graph, and that's the one I'm going to pick. Yeah, so again, I'm going to go through how I would approach making a graph by hand. And we're going to go over multiple levels. All right, so we're asked to make a sketch of this, by hand. Now the function is f of x equals, negative 4x squared divided by 9x squared plus 4. So first we're at the f level. So I start with just f. Now of course for any function, before I go graphing, before I go deciding what I'm going to draw, got to know the domain. Now the domain here is all real numbers. Remember, you can't divide by 0, but this is 9x squared plus 4. So no matter what I plug in for x on the real axis, no matter what real number I plug in, this will never be 0. So I'll never divide by 0, so that's fine. And if there were logarithms, remember you can only take logs of positive numbers. If there are even roots, you can only take even roots of non-negative numbers. Remember the domain, and you just got to remember the domain restrictions for your polynomials, your rationals, your radicals, your logs, your exponentials, your trigs, your inverse trigs. There's all the pre-calc functions you studied. So here are the domains, all real numbers. I can plug in anything. Nothing will make me divide by 0. Then some nice things to know, just to plot some points, would be the intercepts. Now, f of 0 is 0, right? You'd have 0 in the numerator, 4 in the denominator. So 0, 0 is not only the x-intercept, but it's also the y-intercept, and that's the only thing that makes the numerator 0. 4x squared is going to be 0 only when x is 0, and that's it. Now, if there were some other values that gave me an output of 0, I'd find those too. But that's the only point, 0, 0, that's on the x or the y-axis. Any asymptotes? Now, I already mentioned the domain's all real numbers, right? So there's no vertical asymptotes. Nothing makes the denominator 0 here. So there's no vertical asymptotes. But see if there's any horizontals. So this is where you're talking, asymptotes, end behavior. Right? We're also talking end behavior here, limits at infinity from earlier in this assignment. Now, either way you go, right, this is one of those rational functions. So limit as x approaches positive or negative infinity of this function. I'm hoping you see it would be negative 4/9 either way. So y equals negative 4/9 is a horizontal asymptote. As again, this is one of those where the polynomials have the same degree. Just look at the lead terms. This would reduce to negative 4/9. So the graph's approaching y equals negative 4/9 on both ends. And that's really enough for me right now. I guess something else you could also say is, I'll do this for every single level. So here's the x-axis. Let's make a number line for this is f. Now we just set at x equals 0. The output is 0. And because this is squared and squared plus 4 down here, the numerator, will always be negative because you got negative 4 times x squared. Negative numerator always, positive denominator always. This will always have a negative value. Okay, so except at 0, 0, the graph of f will be below the x-axis. So f below x-axis, that's what it means for the value to be negative. On this interval, then it's on the x-axis at 0, 0. All right, that's an x-intercept. And then again, negative values over here, f below, below the x-axis. Okay, and then again, if it were undefined anywhere, which it's not, I would do the limit to the right and left of that to see if you had any, where it was going. If is it going to infinity or negative infinity around those vertical asymptotes. All right, so that's enough stuff said about the original function from just the first level, just looking at the original function as is. Now f prime. All right, so now I'm looking at the derivative. So f prime. So this is what's called the numerator negative 4x squared. I'm going to use the quotient rule for the derivative. So it's denominator times the derivative of the numerator, negative 8x, and then minus the numerator is negative 4x squared, times the derivative of the denominator is 18x. And then all this, divided by the denominator squared. And then we can simplify this a tad. So up top here, this is 9 times 2x. So this has 2x and 4. So they both have this negative 8x factor in common. Yeah, so I'm going to factor that out. Negative 8x times, and if I pull that out, what's left over would be 9x squared plus 4. And if I remove the 2x and the negative 4 here, we'd have minus 18x cubed. This isn't great. Still, that's how I would factor. I pull out negative 8x from both of those, and then we got 9x squared plus 4 squared down here. Now it's quite obvious that 0 is a critical point. And then you find your critical points, right? Where is the derivative 0? Well, obviously, when x equals 0, f prime of 0 is 0, right? And I'll make a number line for f prime. So at 0, it's 0. So they have a horizontal tangent line. And then this being cubic, that's got to be 0 for some value. Now the constant's 4 and the coefficient's negative 18. So I could do some, all right, so I'm going to do this. I'm just going to take a look at where is that expression 0 in Desmos. I know this is kind of cheating it a little bit. Well, let's take a look at that, just that cubic. So I have 9x squared plus 4, minus 18x cubed. So yeah, that's equal to 0 at this value. That's not very nice. But it is equal to 0 at about 0.82. Right, about 0.82. So x approximately 0.82. I got this 0.82 value for that 0. So that makes the numerator 0. And the denominator will never be 0. Again, this is 9x squared plus 4. Now the value of the derivative. Over here when I plug in values less than 0, that'll make this a positive number. And we saw in our graph there that this cubic, right, this is the graph of that cubic, is positive to the left of, 0.82 and negative to the right of 0.82. So when x is negative, this will be positive, this will be positive, positive. We'd have positive values for our derivative, meaning that the graph of our original is going to be increasing up until 0. And then between 0 and 0.82, this will be a negative number, and this will be positive. So I have a negative numerator, positive denominator. This will be negative. So that our graph will be decreasing between 0 and this 0.82 value. And then to the right of 0.82, again, the cubic will be negative. This will be negative. So a positive numerator, positive denominator, you got positive values for f prime. So f will be increasing. And then we'll have local, and then I would say we'd have a local max at 0, 0, right? So this 0.00 should be at the top of a hill, right? Because it's increasing and decreasing. And then you'll have a local minimum at this 0.82-ish value, right? So when I look at the graph later, at this 0.82 something value, that'll be the bottom of a valley, right? A place where there's a local minimum. All right. And then I would look at the second derivative for concavity. All right, so there's my first derivative information. Where's the first derivative 0? Where is it undefined? Where is it positive? Where is it negative? So you can say where the original function is going to be increasing or decreasing. And then you would look at the second derivative for concavity and points of inflection. And honestly, this is all I'm going to write because the second derivative here is going to be a little frustrating. I mean, I would distribute the negative 8x back in, get some degree 4 polynomial, maybe multiply this out. I don't know. Yeah, I'd rather not. All right, so it's going to save some time, and we'll just look at the graphs. I mean, you're going to be at home, but I'm going to just describe to you what you would do normally if you were trying to do these by hand. So where is it? So find the second derivative, find the critical points. Where is the second derivative 0? Where is the second derivative undefined? You make a number line, figure out where the second derivative is positive or negative, and then remember, wherever it's positive, graphs concave up. Wherever it's negative, graphs concave down, curling down. And points of inflection are where the concavity changes, right? So you can also determine where on the graph of the initial does it go from curling up to curling down, or curling down to curling up, where does it change concavity? So again, you may recall from a previous video how to do that, right? So then you're just putting all the stuff we've seen in previous videos about the first derivative and the second derivative together. And the first derivative, tells you where it's increasing, decreasing, so you can find those hills and valleys, points where there's local maximum, local minimum values. And then the second derivative, remember, tells you concavity, which way it's curving, concave up, concave down, and also where those points of inflection are. So you're putting all that stuff together, along with the information about at the first level, where the x-intercepts, y-intercepts, are there any horizontal or vertical asymptotes or oblique asymptotes or whatever. And then you'd put all that together. Now I'm going to punch this in, and I'll come back and look at this and see. All right, so I'm going to put this function in. Right here is the function we were given. F of x equals, you had negative 4x squared in the numerator divided by, and then 9x squared plus 4 in the denominator. All right, so this little thing here, I'll make it a different color. So look, see, it's below the x-axis to the left, negative values to the left of 0. You got the point 0, 0, and then below got negative values to the right. And that's exactly what I said here on the first level. And there's no vertical asymptotes, and it's on the x-axis at 0, below the x-axis to the left is 0, below the x-axis to the right is 0. So that's all happening. We said the only, the end behavior, when we did the limits at infinity, the graph's approaching y equals negative 4/9, right? Now I'll make this like a dotted line and a different color. You see that in the far right, far left, the red graph is approaching this green dotted line, right? Getting closer and closer to values of negative 0.4 repeating, negative 4/9. Same thing on the far right here. The red graph is approaching y equals negative 4/9, right? Approaching this value of negative 0.4 repeating. So all that seems to be happening. All right, and then we said increasing to the left of 0. All right, we're looking at the first derivative information. Going up to the left of 0, going down to the right of 0. So you got this, local max at 0, 0, and you see that here, top of a hill, increasing to the left of 0, and then decreasing to the right of 0. Oh, I made a mistake. I made a boo-boo. I pulled out 2x from this. My apologies. So now this wouldn't be x cubed, and this isn't a value. My apologies. Oh man. Okay. Yeah, I pull out 2x and negative 4, so this would be minus 9x squared. Great, and that would turn this into just 4. So my my first derivative just has negative 32x in the numerator and 9x squared plus 4 squared in the denominator. So 0 is the only value we're at 0. Yeah. Okay, my apologies. So positive to the left is 0, negative to the right is 0. So the only place where it has a hill is at 0. All right. So sorry, I'm not thinking too clearly here. A couple hours in, my apologies again. That would be the first derivative. So then the second derivative wouldn't be that bad, but still, I would find the second derivative, look for points of, where the second derivative is 0, where the second derivative is undefined, and find those points of inflection. All right, so the only hill is at 0, 0. There is no valley, and you're seeing that here. And then the points of inflection look like to be around here, maybe around -0.1, -1 and +1, because it's going from concave up and then switches to concave down, and then around 1 here, it looks like it's going from concave up to concave down to then concave up. And a couple points of inflection that you would find with the second derivative. Okay, so again, my apologies for the mess up there on the first derivative. Just caught this with looking at the graph. That's important to check your work, important to look at the graphs, look at the stuff. So of all these choices, this one doesn't look like that. This one, that's the one I'm gonna pick. And these other two don't look anything like it, right? So I enter my graph, I look at my choices, and just pick the right one. So yeah, so it's gonna go through all the stuff, right? Read through the answer explanations. See domain, x and y intercepts, limits at infinity, asymptotes. Look at the first derivative, find the critical points. Where is it increasing, decreasing? Local extrema. Second derivative, where is it concave up, concave down? Inflection points, right? So they go through all this, and like I said, I messed up. Yeah, see, this was the first derivative, -32x, not what I had. So my apologies once again. I can't apologize enough for that. Hopefully you're clearer headed than I am. And then the second derivative is this. And yeah, so those inflection points would be at not 1 and -1, like I was just eyeballing it, but at positive, wherever this 27x squared minus 4 is 0. So that'd be 4/27, and then plus or minus the square root of 4/27. And you do all that. Okay. So again, I'm just gonna, if the ones with these choices, no, you know what? Just to redeem myself, I'm going to go through this one because this one doesn't look so bad either. It's not, I don't have to use the quotient rule for this one. So let me redeem myself and go make this one by hand and actually draw it out. But then I'm just going to put it in Desmos and make the correct choice from what it looks like in Desmos as well. So f of x equals, this is the opposite of, and then x minus 5 to the 3/5 power. That's an odd root. Remember, this is the 5th root of x minus 5 cubed, so domain's all real numbers once again. So again, I'm at the f level right now. So domain's all real numbers. Nothing's going to make me undefined here. Intercepts. Now, when x equals 5, the output would be 0. Hopefully that's clear. Make a little number line here. So when x equals 5, output 0. And then when x equals 0, I'd get negative 5th root of -5 cubed, so -125, which odd root of a negative. I can pull the negative out. That'd be the 5th root of 125, whatever that value is. But it's positive, right? So to the left of 5 here, got positive values. And then to the right of 5, that'd be positive number to a power, so positive, but then times this -1 out here, I'd have negative values over here. So f will be above the x-axis to the left of 5, and f will be below the x-axis to the right of 5. And then your end behavior. Now the limit as x approaches infinity of this, again, your roots things to powers like this, when if I take a bigger number and bigger number, raise it to powers, this is going to get bigger and bigger and bigger positive, but then you have this -1 out front. So we're going to negative infinity on the right end, and being an odd root with odd powers the other way, limit as x goes to negative infinity. Well, this will go to positive infinity, right? Because the expression here, this would be big negative number to an odd root, odd power. So that's going to be a big negative number, but then times -1 be big positive. So we're going down forever on the right end, and we should be going up forever on the left end. All right, there's my end behavior. All right, so now the first derivative. Now f prime, we do a simple power rule thing here, would be, -3/5 times x minus 5 to the -2/5. All right, so the critical values, so I'm doing x f prime here. This 5 will make this undefined, right? You can't have a 0 to a negative power, which again, you can think of this as -3 over 5 times x minus 5 to the +2/5. So again, 5 makes it undefined. Now, values to the right of 5 make this a negative. So it'll be a decreasing function to the right of 0, or to the right of 5. And then values less than 5. Again, this is, 5th root squared down here, right? There's a numerator of 2. So that's going to be a positive denominator no matter what I plug in, except for 5, and then negative numerator. So I got a negative, so positive, negative numerator, positive denominator no matter what. So a negative overall. So no hills or valleys. The function is going to be decreasing. So it's going to be decreasing until you hit the 0.50, and then, decreasing some more. And then the second derivative would be positive 6/25 times x to the -7, x minus 5 to the -7/5, which again would be 6 over, and then 25 times x minus 5 to the +7/5 if you want to write it that way. So once again, this is undefined at 5, so UND here at 5. But this time these are all odds here. 5th root is something to the odd power, 7th power. So when I plug in numbers bigger than 5, that's positive. So I got positive over positive. So positive second derivatives to the right of 5, meaning f will be concave up to the right of 5. And I plug in values less than 5, this will be negative to some odds. So negative down here, positive up there. So I have negative second derivatives to the left of 5. So f is concave down. So that means there's an inflection point at this 5, 0 point. So I'll put all this information together on the next page, and we'll make a drawing. So again, the only point I know a couple points, right? The intercepts. So say here's 5, 0. There's the point 5, 0. And then I said the y-intercept was at, whatever the 5th root of 125 is. So I know like 3 of the 5th is too big, right? 3 of the 5th is 243. 2 of the 5th. This is between 2 and 3. So again, 1, 2, 3. So somewhere between 2 and 3 is the y-intercept. And using what we know about this, again, end behavior should be going up forever to the left, down forever to the right. So up forever to the left, down forever to the right. Then it's decreasing concave down up until 5, 0. So something like this, decreasing concave down until you hit 5, 0 here. And again, gotta go up forever to the left and go through the y-intercept. Then it's got an undefined, so it's going to be on vertical slope here, undefined slope, vertical tangent line at 5, 0. And then to the right of 5, it's decreasing still, but now concave up. All right, so now decreasing concave up, and then going down forever. So point of inflection there at 5, 0. So it should look something like this. Should look something like this. Now let's take a look at Desmos. And f of x equals, there was negative, and then the quantity x minus 5 to the 3/5 power. So there's your 5, 0. There's your 0. Remember I said it was between 2 and 3, the fifth root of 125. So that's up forever to the left, down forever to the right. And it's, decreasing concave down until 5, 0. And then it turns into, decreasing concave up, point of inflection. So that looks pretty good, right? So hopefully that made up for my little mistake in the last problem. I'm sorry about that. But still, I looked at the graph, look at the choices here. That's what it looks like, that one, right? Not that, not that, not that, right? So the only one that looks like what they had there, what I drew, what Desmos had, was this picture choice one. And again, they go through all the same steps I went through using the original function, right? Domain, intercepts, end behavior, limits at infinity, talk about asymptotes if there are any. Then look at the first derivative, critical points, and where is it positive, negative, tells you where the original function is increasing or decreasing. Then you can say if there's any hills or valleys, local extrema. And then the second derivative, again, critical points, where is it positive, negative? You can say where the original function's concave up, concave down, and points of inflection. And then put all that information together and make a sketch if you wish. All right, so there's another one again with the choices. Now this is a polynomial. This is just a polynomial. So it should have 2, 0, negative 2, 0, and 0, negative 8 as the intercepts. 2 has a multiplicity of 2, so the graph will have a turning point there. It'll bounce off. Has a multiplicity of 1 at negative 2, so it's going to cross over. And it's, degree 3 with a negative lead coefficient, so going up to the up forever to the left and down forever to the right. So let's look at these choices. So yeah, it looks like that. Got 2, 0 with a multiplicity of 2, even multiplicity bouncing off there, turning point. 0, negative 8, for the y-intercept about that. And then negative 2, 0, crossing straight over, up to the left, down to the right. That looks like about it, right? Yeah, this is wrong for the multiplicities. This is wrong for the end behavior. This is wrong for the end behavior. So the only choice that makes any sense for this polynomial function would be this first one. And again, you can go to Desmos and make sure you got the graph correct there. All right, then another one with a rational here. So let's see. Now this would have one of those oblique asymptotes, right? And also at negative 1/3 a vertical asymptote. So possibly this. I think there's possibly all these things. So let's punch this in. So it goes 8x squared over negative 3x minus 1. All right, so the curl is it's up forever to the left on the left end and down forever on the right end. With again x equals 1/3, negative 1/3 would be a vertical asymptote, right? You can't plug that in. And it would have a oblique asymptote, right? Because the degree of the numerator is 1 larger. So I divide these and get, negative 8/3 x plus something. I have to actually do the division. I'll make this like a dashed line here. Again, you can't cross vertical asymptotes. So something that looks like that for the choices. So not this one, not this one, not that one. Oh, there was a minus sign in front. Good thing. I was like, no, those look like it. There was this minus in front, flipping everything over. So now it's got the origin, got this point here. Yeah. All right, so I'm glad I caught that. That's got the origin. Yeah, this one doesn't have the origin on it. So this one is the first. This is the only good one. Because none of the other ones have I mean, this one has the origin on it, but the asymptotes are wrong. The only one that looks like what I have in Desmos there is this one. So again, you could do it all by hand, right? Find that oblique asymptote, take the first derivative, second derivative, and do all that stuff. Just not gonna do that. All right, great. So again, other than that one little error I made on first derivative for that one rational function, um, and everything else worked out pretty nicely. All right, so that's it for the preview of this assignment. Hopefully, watching through it helps you out when you're working on the assignment on your own. And thank you very much for watching.